Welcome to CS1033 Programming Fundamentals, our continuing series of lectures on problem solving. We are going to discuss the searching and sorting area as relevant to problem solving. Let me first give you the outline. So I'll start off with an introduction, and then I will look at two searching algorithms, sequential and binary, and then I will look at a series of sorting algorithms. The intention here is less to do with studying different type of algorithms, but more to do with how different algorithms provide different capabilities. So let's start off with a little introduction. So the activity that we engage in computing is essentially to solve various problems. The data, searching for data and sorting of data are two of the key activities that we engage in when solving problems. Many of the problems can be solved essentially using these two activities, and in many other problem solving scenarios, the searching and sorting would solve a large fraction of the problem. Okay, other fraction very likely get solved using computational work, various solving of equations. Now, when we look at search algorithms, they typically provide a true or false answer to the question if an item is present in a particular collection. In addition to providing that answer, a search algorithm can also provide the location in which an item is present in a collection if it is an ordered collection. So, for example, list is such an ordered collection with a very specific way of indexing, starting with 0, and for a list with n number of items, the last index would be n-1. And when we do a search for an item stored in a list, it can provide the location at which we can find the particular item if it is present. Now, when you consider different algorithms for searching and sorting, they would, now if you take, for example, searching, they would always provide the answer whether a particular item is present or not, and depending on whether it is a ordered collection or not, you will be able to get a location also. Now, these different algorithms have different operational characteristics in terms of the time it takes to give an answer, the amount of storage it uses while running an algorithm to figure out if the item is present in the collection or not, as well as how these performance measures, especially the time taken, behaves. In certain algorithms, you find that for a smaller collection, it is very efficient, but for a larger collection, it is not. Also, if the collection is ordered, that means if it is sorted, then it's very fast. If it is even partially sorted, still it has better performance. But certain other algorithms, when it is sorted, but in the, for example, in the reverse order, will give much worse performance. So it is interesting to actually look for these differing performance characteristics when we are using an algorithm in one of our applications. Now, when you consider both of these algorithms, there is a requirement for a comparison function. So the comparison function, if it is for a search, definitely will have to be the equality, because you would want to check whether a particular item is present. If it is for sorting, you would require a comparison to see whether an item is greater than or less than another item. Moving on to the search algorithms, we have this very simple search algorithm, the sequential search, which can be used to find if an item is present in any kind of iterable collection. So it could be a ordered collection like the list, or even an unordered collection like a set. As long as it is iterable, that means you can iterate over the collection taking one item at a time, then the algorithm can be applied in that. While this algorithm is very easy to understand, very easy to implement, it is of course highly inefficient, because the search is sequential. Start from one end and keep on searching until you find it. Now, when you consider the performance of these kind of algorithms, we essentially look at the number of comparisons we perform, because that is the comparison is the main function performed in the algorithm. That is where the processing cost is concentrated. So when you look at the situation, if an item is present in the collection, best case would be it is at the beginning. So as soon as we start searching, we find it. So best case would be 1. Worst case, it is at the very end. So then the cost would be, you will have to have n comparison. On the average, we can say it is n by 2. Okay, and if the item is not found, the cost is n actually, because until we search the entire collection, we would not know whether it is present or not. So the cost is n. Now I have the algorithm here given in the iterative format. So essentially we have a loop. Okay, so after the initial setting up statements, so there is a cost in this, but it's negligible, happens only one time. We go into a loop. Okay, so this is the main loop. Okay, after the loop, there is some minor instruction execution. That is also a negligible cost. Essentially, here I am returning the position if it is found, and if so, rather than saying true or false, which I can simply say if found true, otherwise false, I am returning the position at which it was found, and to indicate the situation where the item is not found, I am returning a -1. So this is a convention we can use when we do our coding. But this is the part of the code that you should focus on. It is a loop, and within the loop, you have the testing. Okay, so if you really look at the computational cost, you have this comparison. Okay, this comparison happening in every loop iteration. Okay, and in addition to that, there is another iteration that happens here for loop control. Okay, so in effect, it's actually 2 comparisons, and it will occur until an item is found or we have finished searching the entire list. Okay, so so that is the cost factor. Okay, essentially coming from the main search loop. We can look at the same sequential search from a recursive point of view. As you know, if we are developing a recursive algorithm, it will have a recursive case and a base case. So the base case trivially provides the answer. So here's the base case. So if you have a list which is empty, so length of the list is 0, then obviously you don't find the item you are searching for because it's an empty list. Okay, so you straight away return false. Otherwise, you can check whether the item is found at the head of the list. So list index 0 means head of the list. If it is found, we return the result true, so that we have found the item we are searching for. Otherwise, we will be making a recursive call to the function, the same function, and what we do is we are sending the list except the first item now. Okay, so item at the index 0 we have already tested, so now we are sending the rest of the list for checking. Okay, so that is what I'm doing here, sending the rest of the list with the item I need to find. Okay, so this is actually a very, very expensive way of doing a sequential search, as we have discussed earlier. Recursion requires that you do context switching, so pushing your current state into a stack, and when you are returning from the function, then popping the state, which are all very, very expensive computations. So this is just for interest sake. We would not implement sequential search in a recursive manner, but it's quite interesting to see the model, the base cases and the recursive step that we have here. Okay, now let's look at the next search algorithm, binary search. So the binary search is again usable in a ordered collection. The previous one, linear, the sequential search is applicable for any linear storage structure. So that means iterable, but need not be ordered. Okay, need not be ordered. But binary search is for an ordered collection. Okay, it is for ordered collection. So what does that mean? You may have to first sort the contents in the list. So that's how you would get the algorithm started. So let's look at the working of the algorithm. It is again very simple, easy to understand algorithm, and of course, unlike the sequence search, is highly efficient also. Okay, but again, I would remind you, this efficiency comes at a cost, that it is an ordered or a already sorted collection. Okay, so the algorithm simply starts by checking if the middle item in the list is what you are looking for. Okay, if that is not a match, then it will decide whether the search should continue with the left half or the right half of the list. Okay, so this is a classic use of the divide and conquer strategy, as well as implementing it through recursion. So it is divide and conquer because you get a big problem, and to solve it, you divide the problem. So essentially, the problem keeps getting divided into either a left half or right half. Okay, increasingly getting smaller, and at some point it can be trivially solved. Okay. So as I mentioned, the performance analysis, when we do it, we essentially look at the search cost only, but in a program that say you are developing some software, you will have to check the kind of data you are getting and whether pre-processing is required. The pre-processing would be the cost of sorting the collection. Okay. And for a very large collection, that could be a significant cost. And sometimes you might decide it is much more worthwhile to actually use the highly inefficient sequential search. And the idea here is, of course, even if you have a large collection, if you are performing multiple searches in that, the sorting cost is only a one-time cost. Okay, so it's a one-time cost, sorting cost. So then again, no, it may be worthwhile to sort and then use a efficient searching technique like binary search. So when you have to, let's say you have to decide between the sequential search and a binary search. So in problem solving, it is not really obvious. Okay, it's not obvious. You will have to consider multiple factors, such as the size of the collection or which you are doing the search, how often it changes. Okay, because if you take the binary search, you need to have the collection order, and if the so once you do the sorting, no, it's now usable. But if it changes often, then every time the contents get changed, say an item gets added. Okay, so an item removal may not be that hard to handle, but yeah, the adding of an item, because the reason why I said the removal of item may be hard to handle, because you can actually keep that removed item as separate list, and when you search, if you find an item is present but it is also present in the removed list, then you can say that it is not present. But if you are changing values, especially in these lists, you will have to do a resort, which will be a significant cost. So multiple factors will have to be considered in problem solving to decide what algorithm to use. Okay. So looking at the iterative algorithm for binary search, again you can see there is some initial instruction execution that happens. So that's a one-time cost and not a significant cost. And then you have the loop, that is where the computational cost comes. And as earlier, I'm having a small post search cost of deciding to return the position, not just whether you found or not. If that is the case, you don't really need this part. You can simply return the found variable. Now let's focus on the loop. So what we do is, as we discussed just now, we get the midpoint of the list. Okay. So the initial values, the first item is 0, last item is length -1. Then once we get the midpoint, we check if the item is in that location. If it is not, and if the value of the item we are searching for is less than the value of the item stored at the midpoint, we move the search to the left-hand side, the first half. Otherwise, we move to the second half, which is the right-hand side. Okay, and then continue with the search by appropriately changing either the last, if we are going into the left hand side, 0 would still be the first item. The last item would be the mid minus 1. Okay, because mid is the one we check. And if you are moving to the right hand side, then of course the last item remains as it is. The first item now becomes mid plus 1. Okay, so when you are going through a loop, okay, when you are going through a loop, in every iteration, you will do a computation here. Okay, so we normally do not put too much emphasis on this kind of computation, but no, in actual cost computation, you will have to consider that instruction cost also. But here is the more expensive instruction, the comparison. Okay, the comparison that happens, and then if then if we have not found the item there, there is an additional comparison. Okay, there's an additional comparison. So of course, when we compute the cost of searching, well, we will be always looking to find the cost as we move forward. So as soon as we have checked this and it was not found, we have to move forward with our algorithm, which means there is one comparison cost here and a second comparison cost here. In addition to that, through every iteration, there is one more cost here. So so there are actually 3 comparisons happening inside the loop, whereas in the sequential search, you had only 2 comparisons happening. One is on the control loop control, and the other one on the equality comparison. Okay, so so be mindful of that. While we tend to say binary search is very efficient, when you get down to the details, you find that no, maybe for small list it is not efficient. Okay. So this is the recursive version of the binary search. As again, here we have the base cases and the recursive case. So of course, if the list we get to search is empty, that means a list of length 0, then we would return false, because that means we have come the end of the list, and no item has not been present. Otherwise, we get the midpoint. Okay, we get the midpoint, and if the item is present at the midpoint, we return true. So these are the base cases. On the alternative, that means if we have not found it, we will call the search function again recursively. Using the split operator, we can send the left hand half or the right hand half. Okay. So of course, when we do that, we will be only able to return whether we found the item or not the position. So that's again another very important situation. We can actually get the position, but in a very convoluted manner. So if the position is required, not just whether the item is present or not in a collection, then sequential search is quite attractive option. So yeah, so this is where the recursion version of the algorithm is running. I have some examples here. So if I'm searching for 3, then when I get the midpoint, which would be 13 here, it is not matching with 3, and because 3 is less than 13, we restart with the left hand side. Okay, and then when we search, in this we will get 2 as the midpoint, okay, because we have an even number of items. Then when you search, it doesn't match with 2, and because the item 3 is greater than 2, we will continue with the right hand side, which is what happens here. Okay, and yeah, of course, then you find that no, the item is not there. So what you get next is empty list, at which point you return false. The other two are when you have the item present. Okay, so here's the performance which we are giving in the time complexity measure. So mind you, we use what is called the big O notation, Okay, it's called the big O notation, right? And what happens here is you can see that the base case is given for the sequential search, and then the worst case n, but you can see average, which used to be n by 2, is given as n. So here this is the order. Okay, n by 2 is essentially 0.5 times n. So the order is, it's in the order of n. Okay, so that's why while when you do a very specific calculation, the average would be n by 2, but in the big O notation it is n. And when you consider binary search, best case obviously is when you search in the first time you check in the middle, you find it. So that is obviously one. Otherwise, if you consider the worst case, you will be dividing the list by half every time. Okay, so the number of times you can divide that is given by log n. Okay, so if you have, say, 16 item list, okay, you can divide that first to 8, then to 4, then to 2, like that. So you will be able to divide it 4 times, okay, which is actually 2 to the time. So for a 16 item list, what you have, 16 is 2 to the power 4. This is how we get this. So we get 4 levels. So then that's log of 16, okay, to the base of 2. So that will give you, you have to do the search 4 times. But this is actually not a correct calculation, because as you saw, within each iteration, within each sublist, we have to do a 3 comparisons. Okay, whereas sequential search does 2 comparisons, the binary search would do 3 comparisons. So this is essentially the sequential search. It is 2 times n. If you look at the actual cost, if you give it in terms of comparisons, 2 times n. In the binary search, first time you would do 3 comparisons into half the length. Next, 3 comparisons into quart of the length, and in that manner, not in diminishing manner. So and the number of times you do that is the log gain. So the order of the cost is then log gain, because log gain is the value which is multiplying the rest of the equation. Okay. Okay, so moving forward to the sorting algorithms. So a sorting algorithm, as noted here, will just reorganize items into some order. So that order could be the alphabetical order, numerical order, or the length of items, some intrinsic property. Okay. So that has to be decided by whoever is implementing a solution to a problem. Okay, what the order is. So when you are looking at the performance and cost of these algorithms, there are 2 operations to consider. Unlike the search, which only where we only in which we only consider the comparison operator. Here, apart from comparing the items, we also have to do a rearrangement. We have to shift items. Okay, so sometimes it can be done by shifting, but most often it is done by a swap. Okay, so 2 items are swapped in their locations, right? So when you consider the overall cost of sorting algorithm, you have to take into consideration both the number of comparisons and the number of swappings that have been performed. Okay, so this kind of different this kind of performance criteria allows us to evaluate different type of algorithms. Okay, so let's look at the very simple algorithm bubble sort. So in this one, this algorithm, it simply makes multiple passes over a collection. Okay, and in each pass, it will perform a computation which partially sort the collection. So the computation does is to get the largest item in the current list. Okay, in the current list to the top, or the correct position in the list. So once you do that, once you have the largest item in the correct position, you get the rest of the list and redo it. Find the next largest one and put it in the correct position, and so on and so forth. So ultimately, you have the whole list sorted in that manner. Okay, so this algorithm will make n-1 passes, because in an n item list, it will go through this n-1 times, and each time it will do the number of comparisons equal to number of items in the list, but of course this is now diminishing. So the total number of comparisons would be n-1 plus n-2 plus n-3 plus, like that, up to 1. Okay, so 1 to n-1, the sum of the numbers, which is which can be written in this manner. Okay. So if you consider the sorting algorithm, consider scenario of already sorted list. Okay, so the list is already sorted, and you tell bubble sort to sort it. So there won't be any swapping because it's already sorted. Okay. What is the worst case? Worst case is giving giving a list which is sorted in the reverse order. So now every time there will be a swap. Okay. So this is how we visualize the best case and worst case scenarios for the bubble sort. Okay. So one interesting improvement you can do it. Suppose when you are sorting a list, in one of these rounds, you find in that round, you did not do any swapping. That means all the items are now in order. So you may not have gone through the full number of iterations, but it is no longer required. So that is one way in which you can terminate the sorting operation early and gain a performance improvement. So here's the bubble sort algorithm. As you can see, there are two loops. In the outer loop, we go through the loop, the length -1 times. Okay. So if there are n number of items, we go n -1 times this loop. Of course, we go through the loop in the decreasing order, first getting the full list and then getting the biggest item there and putting the correct position and then making it just one item less list like that. So that is what the outer loop does. Then in the inner loop, we will compare adjacent items, and if the item to the left is greater than the item to the right, then we have to do a swap. So these three instructions are for a swap operation. Okay. So you can actually now look at the cost involved. There are these are the comparisons that happen. So every time a comparison returns true, you will do a swap operation. Swap operation is very expensive. Okay, so actual cost is comparison plus the swap. Okay, so we can say, for example, on the average, half the time the swap will have to be done. Let's say on the average half the time. Then yeah, so anytime you have a particular I number of comparisons happening, I by 2 number of swaps will happen on the average. Okay. Right. So that's how you would want to compute the cost in a detailed manner. Next one is the selection sort. So selection sort algorithm is an improvement on the bubble sort. So as you have seen, when we go through the inner loop, we keep on doing swaps. Okay, but this swapping is done so that we take the largest item to the correct position. Okay, so what happens in selection sort is we don't do this swapping, but we keep track of where the biggest item is located. Okay, so that's what it does, keep track of the position of the biggest value when you going through the list. So it could be part of the list, but as you go through it, you keep track of that, and once you have tested every item in the list given to you, you do a swap. Okay, if the biggest one is not already in place, you swap whatever is in the correct position with the largest value. Okay, so that greatly reduces the number of swap operations you perform. Okay, you don't reduce the number of comparison operations, but you reduce the number of swap operations. Right. Okay, so that's what I'm saying here. That same total number of comparisons will happen, but the swaps will get. There's a potential for swaps to get reduced. Okay. So here's the loop, just the same as bubble sort, except that so here's the outer loop. We go through it, and in the inner loop, when we find a item which is the larger than which is the currently the largest one, we keep track of that. Okay, we keep track of that. This would be the item that is currently the largest, and we keep track of that. And then the loop actually ends here. Loop ends here. Earlier we had the swap also within the loop. Now swap is outside the loop, so it happens only once for the inner loop. For the inner loop, it only happens once. Okay. Of course, for the outer loop, it happens that number of times. Right. So here I have a sample output when you run this program with appropriate print statements. Okay. So I have left those things as exercises for you to figure out where to put the correct print statement to get an output like that. Okay, so here you can see that it first pick the largest one and puts in the correct position, and then pick the next largest one and puts in the correct position, so on and so forth. So next, we want to look at the insertion sort algorithm. Okay, so the way it works is it keeps a sorted sublist in the lower part of the list. Okay, so think of the situation where you have a list unsorted. Okay, unsorted list, and you start sorting it by making sure the lower part is sorted. So right, so you can start with a single item. Okay, so single item is sorted. Okay, because it's a one item list, and then you add one more item, and then you sort this. Essentially, you make the smaller one go to the left and the bigger one remain the right side, and then you take the next item, and again you do this. Okay, so one by one you make sure that no, the lower part of the list is sorted, right? So the once you pass to the entire list, you will find now the entire list is sorted. Okay. And the insertion sort, it could be the worst case scenario is where you will be doing comparisons every time. Okay, so when you have a list of n items, no, it could be like the bubble sort being done. Okay, with just the comparisons. So you will have first you will have n-1 comparisons. Second, you will have n-2 comparisons. Third, you will have n-3 like that. No, so those comparisons will add up, and this would be the worst case total for the comparisons for a list of n items. Okay. Best case is no. no, only one comparison, because you find the current, the newly picked item is larger than the current largest. So you just put it, or you just leave it where it is, and no swapping or anything is required. Okay, so that way, you will only do n-1 comparisons, and so the list is sorted. Of course, this happens when you try to insertion sort an already sorted list. Okay. So here's the algorithm. Okay, so you would go through the full length of the list. So that is the outer loop, and within that loop, you decide the current highest value. So you initialize with a value, and then while so you have while loop. So you would search from the 0th location, that is the start of the list, to your current the position that for the current position, you get a value. Okay, you get a value and check whether it is greater than the current value. Okay, so this is that loop where you try to keep the bottom half sorted. So what happens here is actually you are doing a shift operation. Okay, so you can see this is a shift operation. So if I were to put a comment here, this is the shift operation. Okay, because you find that this item, okay, this particular item at position position post -1, okay, is greater than the current value, which means you have to make this value the current value. Okay, which is what you are doing here. Okay, but before you do that, you have to shift all the values one place to the left. Okay, so you are now doing that shifting. Okay, so that way you make space for this current value at the top of the list. So once after you shift, you would place the new largest value is placed at the top of the ordered part. Top of the ordered part. Right. So I have noted here that shift operation is much more efficient than swap operation, because shifting requires only a single assignment, whereas swap requires 3 assignments. Here's a sample run of the insertion sort. Right. So let me show what is happening here. Right. So this is your input. This is your input array. Okay. So we just take the first one, say, and it's sorted because it's a single element. Then we take the next 2. Okay, and obviously we'll have to now swap these 2. So that's what happens here. Okay, then we take the next one. Okay, and we find no swapping is required. It is in the correct order. Then we take the next one, 17, and we find that it has to go to the beginning, which is what happening here. And then we take the next one, 77, and we find that it should go between 54 and 93, which is what happens here. So on and so forth. We keep the this left side sublist sorted always. Okay, sorted always, and by the time you get to the full length, full list length, you would have the whole list sorted out. Right. Next, we will look at the shell sort algorithm. So this is an improvement over the insertion sort. Okay. So insertion sort we did by taking the full list. Okay, and sorting by keeping the lower part half or lower end sorted. In shell sort, we do the same thing, but now what we do is we take the original list, break it into a number of smaller sublists, and each sublist get sorted using the insertion sort actually. So rather than just using only a single list for sorting like what we did in insertion sort, here there will be a value called the gap to create the sublist. Okay, so so let's say you have number of items. So I'm just going to type here 1, 2, 3, 4, 5, 6, 7, 8 like that, and you can take a gap of 3. So you put together sublist by taking 1, then the third item 4, okay, 1, 2, 3, 4, 5, 6, and then 7. Okay, so item 1, 4, 5 would be one of the sublists, 1, 4, 5. Similarly, items 2, sorry, items 1, 4, 7. Okay, and 2, 5, 8 would be another sublist, and the third one would be 3, 6. That's all. Okay, that's a sublist. So now you will take these sublist and apply the insertion sort. Okay. So now what will happen is when you do it, when you do your sorting in this manner, none of the sublists will have their items in the correct final place, because now you are only sorting within a sublist. Okay, but because it's anywhere sorted list, partially sorted list, the items are now getting closer to their correct position. And finally, if you do a insertion sort with just the increment of 1, that means you basically take the whole thing and do a insertion sort, then you get the finally sorted list, right? So if you analyze when you analyze the shell sort algorithm, you will find that this use of sublists actually reduce the total number of shift operations. So here's the algorithm, right? I have simply divided by 2 the length to get the sublist count. Okay, but you can use any other form of creating sublist, and then the algorithm will get the sub list and do what we call the insertion sort on that particular gap or the sub list. Okay, so we give the list and starting position and the number of items in the list, so then it will get sorted. Okay, and so this is the sorting main sorting algorithm. Okay, with the loop. So the gap insertion sort is defined here. So this is similar to the insertion sort. So you get a set of items defined by this gap, and then you do the insertion sort on that. Okay. That's the technique. So here we have the example of running program. Okay, so let me use this example to make it clear to you what is happening here. Okay, now this is the original. This is the original input. Okay, right, original input list, saying you are basically saying sort this particular list and use a sublist size of 4. Okay, if the sublist size is 4, you essentially have the 54. So 1, 2, 3, 4, then 77, and then 1, 2, 3, 4, and 20. Okay, so that is one of your sublists. The next sublist is 26. And 31, okay, because so after the first one I'm starting the second one, then again after 4 elements the next one. Okay, and after 31 there is 26, 1, 2, 3, 4, 31. After 31 there's no another item. Okay, and the next one is 93, and the next item is 1, 2, 3, 4, 44. Okay, 44, and next it is 17, and next one will be 55. Now we are done with all the items. Actually, no more items. So what you do is you sort these sublists. Okay, so this one would get sorted into 20, 54, 77, because that would be the correct sorted order here: 20, 54, 77. Okay, and this one would get sorted into 26. Nothing happens, it is already in the correct order. And this one will get sorted 44, 93. Okay. And this one is already sorted, it is in 17. That's the order. So if you look at end of the sorting operation with the sublist size 4, you should get this output. Okay, that's your output. Let me put a line there. This is what you should get. Okay, and and you can see when you go down like that, 20, 26, 44, 17, 20, 26, 44, 17, you get that list. Okay, 54, 31, 93, 55, You get that one, and then the 77. Okay, so that's how the sorting happens. Then we reduce the size to 2, and then finally 1. So when you have the size of 1, it is essentially what you have is the direct insertion sort. Okay. Now you might ask, no, why don't we just do the insertion sort like that? But no, the because of the way you do things, no, the number of shifts will get greatly reduced. Okay, so that way you will have a major performance boost. So that is the cell sort. So I have the illustrated example here, just similar to what I have explained right now. Then next we look at merge sort. This is a recursive algorithm. We have looked at this actually earlier, so I will not spend much time on that. So this one will continually split list into half. Okay, so a classic case of of a recursive algorithm. Okay, so the base case is when you have a list which has only one item or empty, then it's sorted. Okay, if so, to get to the get to this base case situation, you keep on splitting the list you have. Okay, and once you have got to a sorted scenario, so that would be either list or the sublist is empty or it has only one item, then you start to back up and do the merge. Okay, do the merge. So when there are two halves which are sorted, you can do the merge operation, right? So when you analyze the sort algorithm, you have to consider how many times a list can be divided like that. So we know that to be log n. Okay, when you keep on dividing, you can go to the depth of the division, which is log n. Okay, and then the other operation of interest is the number of operations that you are required to perform to merge. Okay, so that is in the order of n. So we generally say the resulting the total number of operations is n times log n. So here's the merge sort given in recursive form. So you are given a list and asked to merge sort it. What you do is you split the list. So you get the midpoint, okay, by getting the length of the list and do an integer division on that. And then you can have the left half and the right half. So left half means up to the mid. Okay, so 0 to mid minus 1 would be the left half, and then mid to n minus 1 would be the right hand side. Okay, so if I may write, so this left is from index 0 to mid minus 1. Okay, and right hand side is mid to n minus 1 for an n item list. So that's what we have here. Then we do the merge sort on the left hand side and merge sort on the right hand side. Okay. So once you have the sorting done, you have to do the merge. Okay, so so split. Let me note it down. So do the split. Okay. You can do the split only if the length is greater than 1. Okay, otherwise you can't split. If length is greater than 1, split, then do the merge sort on the left hand side and right hand side. These are recursive calls. Then do the merging. Okay, this is where you do the merging. Okay, so the merging loop goes to the other side. Okay, so while loop. Okay, so I had some notations left over from the earlier discussion. So there you do the merging, right? So I have written an output you get for a sample input. I have another diagram which shows the, yeah. So here's the splitting happening. Okay. So this is the original list, right? And so initially it gets split at that point, and then you have this one, and then this one gets split at this point. So like that. So you will continually get the list split until they are split into individual item list. So this is an individual item list, so it is sorted. Okay, then you go back up the tree, merging. Okay, so here, so this I have inverted this tree now. Okay, so this tree I have inverted for better visualization. Okay, and so this is the merge. So when you are doing the merge, you make sure it is sorted. Okay, here again you do a merge and you make sure it is sorted. Here again, no, it is in the sorted order. And then you would merge these two. Okay, right. So this is actually quite straightforward to do it. You take the first one here, and you have basically two lists, and you take the leftmost of the first list and the leftmost of the right list, and you take the smaller of that, and put it as the first item. Okay, as the first item. Then you remove this one. Okay, you remove this one, and you have this list 26, 54, and 93, and then from that you again get the leftmost one. So it will still be 26 here, and this will be 93, and you find the smaller one is 26, so you just put 26 there. And then you get the next left hand side value, this 54, and then you have the 93, and you would compare and see that the 54 is smaller, so you put it there, and the next time you have only a single element left. Okay, so you just put it here. Okay, so that's how the merging happens. Okay, splitting and merging. Okay, right. Next, I want to discuss quicksort. Okay, these again divide and conquer strategy based algorithm. Okay, here of course the splitting is done So for example, remember binary search. So you split in the middle. Here, of course, the splitting is done around a value. Okay, and that value we call the split point. Okay, so split point is somewhere in the list. Okay, um, so when we get the algorithm started, we can use any point in the list as the split point. Okay, we can just take always as a standard the first value in the list. Okay, first value in the list. Okay, and then you have the list split, and the sorting action will proceed. Okay, so let's go and look at that operation. Okay, so here, okay, you have the quicksort function. It gets a list, and to mark out part of the list, we send the two indexes, first and the last. So mind you, we are always sending the same list when we are calling the function, but interesting thing is we will define a sublist in the lengthier list by simply indicating. So we have the full list. We will indicate the first item is here, the last item is here, so that it will give a sublist. Okay, so that way you have a sublist. So we have a algorithm to do the partitioning. Okay, so the partitioning will, once you give this list, it will return to you the point at which the splitting should occur, and based on that point you will again call quicksort. Okay, this time so always you pass the full list, but no, define where in the list is the sub list. Okay, so the first quicksort will take the left hand side first to split point -1, and the second quicksort will take the right hand side split point +1 to last. Okay, so that's how actually the quicksort algorithm works. Okay, so that's all to the quicksort algorithm, and then we have a separate function to do the partitioning. Okay, right. So I would like to suggest that you have a detailed look at the algorithm. So our intention here in this discussion is how to use these different algorithms for problem solving purposes. Okay, so as you can see here, this particular algorithm is a recursive algorithm that uses divide and conquer. Okay, so you get a bigger problem to sort, and then you make it into two smaller problems. Okay, right, and then you proceed. So let me show you an example here. Okay, the original, okay, this is the original list that is given to you. Okay, and you are given the first item as 0th location, and the last one as the 8th location. So this is actually 0 to 8. This is a 9-element list. So you get the full list, and you partition at the 5th position, 0, 1, 2, 3, 4, 5. Okay, here. and then you take this value and you will now swap with this one. Okay, you check with the first one, and you find that 31 is smaller than 54. Then you will swap. Okay, you swap 31 with that value. Okay, and then you will get a new new sublist, no, 0 to 4, 0, 1, 2, 3, 4. So this sublist is what you are going ahead with, and that gets partitioned at 3. Okay. So this is a recursive calls that are happening. Okay. So first of all, I am going on the left hand side, because if you look at the algorithm, okay, you split and then you call quicksort, and then you come here, you split again and call quicksort, and like that until you are done with the left hand side, and then you return from the left hand side and go to the right hand side. Okay, so that is what is happening here, and then you partition. Sorry, so you came 1, 2, 3, 4, 5 up to here, and then you will partition at this point 3. Okay, and so it's 17, and you compare with the first one. Okay, it is larger, so you do a swap. Okay, so 31 comes here, 17 goes there. Okay, and now you get another half of the list, 0 to 2. Okay, so this would be the sublist, and now you are partitioning at 0, that means 17, so nothing more is done, leave it as it is, and thereafter nothing more to partition. Okay, nothing more to partition. So these first and last values you can check in the algorithm how they change. So at one point this value will become no, a negative value or a 0, and which point it says no more partitioning to be done. Okay, and then you basically have this type of sorted sublist, sorry, sorted list, partially sorted list, and then you no, return. Okay, so earlier you had 0 to 2, and you partition at 0. Okay, so let me type that. When you had 0 to 2 here, okay, 0 to 2, and when you did your partitioning at 0, the remaining part of the list is 1 to 2. Okay, so it is that 1 to 2 that you get later. Okay, let me put these ones also into proper situation. So this is 0 to 4, and when you partition at 3, okay, the other side that gets remaining is 4. Okay, right, the right hand side. Okay. So my notation is the left hand side list, the pivot point, and the partitioning point, the pivot value, and then what is on the right hand side. And when you consider this one, 0 to 8, okay, 0 to 8, and when you partition at 5, then on the left hand, right hand side, you will have 6 to 8. Right. So let's see what happens here. Okay. So you can see now when you are returning from your left going partitioning. So at this point you are returning, then you will return to the right hand side. Okay. And when you are returning, and then you will of course again get a pivot a partitioning point at 2. That means on the left hand side you will have 1 and 1, and on the right hand side you have nothing. Okay, so this is again you are going in the left hand side. Okay, and so there will be no more partitioning there. So that is how we proceed, and you can see that the 4 and 4 is given here, and then 6 and 8 is given here. Okay, so these are the so the recursion goes in the left hand side first, and then returns and goes in the right hand side. And when you are going the right hand side, again you might go in the left hand side within that. Okay, so that is the recursive call that is shown here. So continue to the next one, the heap sort. Okay, yeah, so this is the final sorting algorithm I want to discuss with you. So this is based on a data structure called binary heap. Okay, and when you look at what a binary heap, first of all you have to understand the data structure called the complete binary tree. Okay, because the binary heap data structure is based on the complete binary tree data structure. And a complete binary is a binary tree. We have already discussed binary trees, okay, in our previous part of this lecture series. And how does a binary tree becomes a complete binary tree? Well, in every level except the last level, okay, the filling of nodes are happening to the left. Okay, so so when you start with the root, you will fill the child nodes, and say you get 2, you will fill like that, and then if you get another 2, you fill the left first. Okay, and if you get another, say, 1 item, then you fill the left like that. Okay, and if you get another 2, then you will fill this. Okay, it's a binary tree, and then you fill it here. So always you are now creating the binary tree or creating these nodes going to the left. Okay, going to the left. And another aspect of a okay, so that's how you get a complete binary tree. Okay, so from a binary tree, you get a complete binary tree, and then this complete binary tree becomes a binary heap. Okay, which is what we are looking to create when the items are ordered in a specific manner. What is this specific manner? The value in a parent. Okay, so if you take the if you take a parent node, let's say this one, the value, okay, so it has a value, no, it is no, if it is greater than the values of the two children, then this is called a max heap. If this value is less than the two children, it is called a min heap. Okay. So binary heap can be either a max heap or a min heap. Okay. So for our algorithm work here for heap sort, we are using a max heap. Okay. So so that is how you get to a binary heap, and this binary heap can be while it is a tree structure, it can be very efficiently stored in array also. Okay, so it can be used either as a binary tree or as an array. In fact, for our work, we will be using an array. Okay. Okay. So in this array represented in the binary heap, so you essentially have a list. Okay, you have a list, and then you will store items. So you store the root in the first one, and then the second and third are its two children, and then for this particular element, its left and right will be here. Okay, and next two will be the left and right for this particular so this one would be here and here. Okay, left and right. Okay, so like that, we can represent it as an array. There's a simple way to get to these elements. So if the parent node is at index I, its left child is at 2 times I plus 1. And the right one is next to that. So it will be 2 times I plus 1 plus 1. So 2 times I plus 2. This is when indexing starts at 0, which is the case for all the list data types. Okay. So rather than using the binary tree structure, when you use a array or this kind of a list, it is much more efficient. Okay, much more efficient in terms of storage usage. And yeah, the heap sort has quite big similarity to selection sort, in that we first try to find the minimum value and then shift to the beginning of the list. Okay, so so here's the algorithm. First of all, we build a max heap. Okay, so we build a binary heap data structure. Okay, so what we do is we build a binary heap data structure of the type max heap. Okay, and when you do that, initially when you do that, we will have the largest item at the root. Okay, so that's what happens when you build a binary heap. Okay, of the type max heap. Okay, then you can say that, okay, now I have got the largest one, and then you can proceed to reduce the size of the heap by 1. Okay, and redo the same thing. Then you get the next largest one, and again you reduce the size of the heap by 1, and then you get the next largest one. Okay, so that's how you would proceed. So always so we talk about this heapification. Okay, that means
converting the binary tree into a binary heap. Okay, to do the to be a binary heap, of course, no, as we have given in the definition, and to be a binary heap of the type max heap, the parent must have a value which is higher than both the left and right children. Okay, so then of course those children must be no, heapified, as in that particular child should have value higher than its own child or its own children. Okay, which would be grandchildren of its parent, right? So therefore actually this heapification start from the bottom and works upward. So here's the algorithm for the heap sort. Okay. Right. So we have a algorithm for heapification where you give a list and the size of the heap as n, and an indication where the current root of the particular subtree for heapification. Okay, and then this particular set of codes make sure that the child the children have values less than the parent. Of course, essentially you swap them if there is a larger one, and then you can recursively heapify the tree. Okay, binary tree. And then this is the algorithm for heap sort. You would build a max heap. Okay, and then you would once you have built the first one, then you go into a loop, and until you are done with the number of items in the list, you would do this swap between what is at the zeroth location, at the first location, and what you have currently taken as the root of the subtree. Okay, so that root of the subtree currently has the biggest value, which you would swap with the value at the zeroth location. Okay. So here I have the kind of a partial representation of what is happening with the heap sort. So this is the input. Okay, this is the input. Right, you can see the input, and you would build a max heap. Okay, that is a binary heap of the max heap type. Okay, so you should spend a little bit of time drawing the binary tree structure at each level, and see how the values get switched, so that the tree gets heapified. Okay, so for example, if you take the input that you have here, okay, so you start with 54, then you have 26 and 93. Okay, so these are the two children, okay, of 54, and then you have for 26 the children 17 and 77. Okay. And then for 93, you will have 31 and 44, okay, as its children. 31 and 44. And then you have 55. Okay, so 54, 26, 93, and then 26 has 17, 77, and 93 has 31, 44, and then you have 55, 20, so that it would go to the left hand side. Okay, 55, 20. So I'm trying to draw the binary tree for you here. Okay, so like that. And yeah, so that's how you would create, but this is not heapified, because in heapification you will have for any inner node, that means a parent node, it will be larger than the child node. So if you take this now 55, 20 and 17, if you switch 17 and 55, no, it satisfies the requirement. Okay, because swapping 20 and 17 won't do it, because at the lower level the bigger one is 55. So you essentially swap these two. Okay, you essentially swap these two. Okay, so 55 will come here, 17 will go down. Okay, so you can see that happening here. Now 17 and 20 are the lowermost ones. Okay, and then you have now here 55 and 77. Now that will not work, because this will have to get swapped. Okay, right. So 77 and 26 should get swapped. Okay, and then so the 77 will be here, and then 93 and 54 should get swapped. Okay, here. And here, of course, it doesn't matter, because what gets down here is 54. 54 is still larger than 31 and 44. Okay, so 31 and 44 will remain as it is. Okay, remain as it is here. Okay, so this one will remain as it is. This one we change by a swap. Okay, and then 26 have come here. Okay, and 55 has come here. So that is those two. Okay, and then yeah, 77 has come here. Okay, this 77 has come here, and then the 93 got swapped there. So 77 and 54 are the other two children, and then 93 has gone to the top. Okay, so I'm just showing you how the max heap is built. Okay, so first of all, you just build a binary tree, then you do the heapification, which is to make sure that always for a given inner node, which is a parent, that parent has a higher value than its two children. Okay, and from bottom up, it should be the way all the way up to the top. Okay, so once you have this binary heap built, so this is your binary heap. Once you have that built, then you can do the you can progressively do the sorting. Basically, you figure out what is the largest, and then it is going to be at the root, okay, of the subtree, and then you will get the next one and put to the subtree. So it will progressively get sorted. Okay, progressively get sorted. So that is the sorting part essentially. Okay, so that is how the heap sort works. Finally, I have a summary of the performance here of the algorithms. Okay, so let's consider the average cases. So you can see bubble sort, selection sort, insertion sort, all three have big O notation based performance values which are the same, but we know that in reality these are only approximations. Big O is approximation. So selection sort is faster than bubble sort, and insertion sort could be faster than the bubbles selection sort. Okay, like that. And then merge sort, quick sort, and heap sort are all n log n, whereas cell sort is n log n square. So those are the time complexities. I have an exercise. So the slide set has all the code for the different algorithms, both the searching and sorting. So the task you have to do is to implement these algorithms with some additional code. Okay, so you have to import the time library and time the calling before calling the function. Okay, before calling the function, take the starting time, and when you return from the function, get the ending time, and then you can create actually a table of this performance data. Okay, make sure that there are no print statements within your function, because you will be calling a particular function. You are calling the function, it will be actually here, and make sure that the function does not have any print statements inside, because if you have print statements, then it will skew the runtime, because executing a print statement takes a longer time. Okay, so that is the exercise we'll do. So this discussion we had was on searching and sorting algorithms, which are a big part of our toolkit for problem solving. Okay, so think of us having a toolkit to deal with a problem. So you are going towards the problem with these tools, and one of the two very important tools would be searching tools and sorting tools. Okay, so if you take a screwdriver set, I'm sure you are familiar with that. We have different screwdrivers for different type of screw heads and for different applications. So like that, we will always have toolboxes with tools doing the same thing. For example, searching or sorting, but different varieties to fit into different requirements we have for the problems we are solving. Okay, so that concludes this part of the lecture. Thank you.